Let's consider the following example. We have a U manometer, and this U manometer is on top of a cart, and the cart is accelerated with constant acceleration A. We are asked to find an expression for the acceleration A in terms of the geometry. So the geometry will be L, the distance or the difference in between the two heights of the level of the fluid, the fluid characteristic, which is given by the density, and the gravity. So in other words, we are asked to design an accelerometer with this. Okay, so let's analyze what's happening in the bottom leg of this manometer. So at the bottom we have, let me do it here, so I'm going to isolate it. So let's assume that these have an area of A. So on the left hand side we are going to have a pressure. I'm going to call this pressure pressure 1, and in the left hand side we also have a pressure, and I'm going to call this pressure 2, and also the same area holds. Now this is L, and if we apply Newton's second law to this manometer, we are going to have, okay, and why Newton's second law? Because the sum of the forces is equal to mass multiplied by the acceleration. So that's it. The forces are the ones given by the pressure on the right and on the left. So on the left we have positive P1 multiplied by the area. On the right hand side we have the pressure on 2 multiplied by the area, and it's on the opposite direction, and that should be equal to mass times acceleration. Now the mass is the mass of the water that we have inside. So the mass is equal to the density multiplied by the volume. Otherwise, the density multiplied by the length multiplied by the area. So if I replace this expression in our previous one, we have that P1 multiplied by the area minus P2 multiplied by the area is equal to the mass, which is rho L area, and multiplied by the acceleration. Now we can cancel the area in all the terms, and therefore we can solve for A. Solving for A, so we have P1 minus P2 divided by rho divided by L. So the acceleration is P1 minus P2 divided by rho L. And so this is our first equation. Now we need some expressions for the pressure at 1 and the pressure at 2. So we can use what we learned before about manometers. So we can tell what's the pressure in this point compared with the distance, let's call it H1, and the pressure at this point if we look to this distance, which is H2. So this is 0.1 and 0.2. So for using hydrostatic pressure, at both sides, we have that P1 is equal to the pressure at the top, and the pressure at the top is equal to 0 if we consider atmospheric pressure and manometric pressure. So that's P1 is that pressure plus the weight of this column. So that's it. Atmospheric pressure, which is 0, plus gamma multiplied by H1. And P2 is equal to the atmospheric pressure, which is 0, plus gamma multiplied by H2. So P1 minus P2 is equal to gamma multiplied by H1 minus gamma multiplied by H2. Otherwise, gamma multiplied by H2 minus H1 minus H2. And replacing in equation 1, we have that the acceleration is equal to gamma multiplied by H1 minus H2 and divided by rho L. Now gamma is equal to rho multiplied by the gravity, so this is, and we are dividing by the density, so we have that rho multiplied by the gravity, H1 minus H2, and H1 minus H2 is H according to the drawing. This is H1 minus H2 and divided by rho L. So we can cancel a few things. So this rho is cancelled and we'll replace this by H. So we have that the acceleration is equal to rho, the gravity multiplied by H and divided by L. So this is our accelerometer. So we can measure the acceleration by looking into H, this distance, and multiplying by the gravity and divided by L, which is this distance.